Good morning, students. Today we will be studying about the uh, black body spectral distribution as explained by Rayleigh and Jean. Okay, on the basis of classical mechanics theory. Okay, so this graph you already know. Okay, the energy versus wavelength distribution. It shows a pattern like this with different temperatures T1, T2, and T3. You are seeing that the graph, the black body radiation spectral graph is moving towards the lower wavelength. This was explained by uh, scientist called Wayne, isn't it? We saw that Wayne's displacement law, that with the increasing temperature, the wavelength is moving towards a lower region, isn't it? So Wayne's law could hold good in the lower wavelength side, whereas Wayne's law could not explain the spectral distribution in the higher wavelength. Okay, this is the higher wavelength side. Okay, so the problem lies here. So in order to explain this discrepancies of the explanation of the spectral distribution of the black body on the higher wavelength side, Rayleigh and Jean, they tried to give their own explanation. Okay, is that clear? Wayne's law could explain the spectral distribution of the black body in the lower wavelength side. This is the lower wavelength side, this region. Okay, and in the higher wavelength means when the energy is reaching to its peak, why does it decreases? Okay, what is happening in this side of spectral higher wavelength region could not be explained properly by Wayne. Okay, so Rayleigh and together with Jean, they try to explain this. They try to have their explanation on the classical mechanics way. And so we are going to study about the Rayleigh-Jean's way of explanation of the spectral distribution of black body. I hope it's clear now. So we will move on to this explanation. Okay, so they consider a black body. Okay, so they consider a black body to be inside a cubical box with a length of A, okay, and with the boundary of x is equal to 0 to x is equal to A. Okay, imagine that the black bodies are inside a cavity, and these walls are very non-conductive walls, means the black body radiations that are emitted within this side inside are not allowed to go outside. Okay, they are stopped at the walls in the boundary of x is equal to a to x is equal to 0 to x is equal to a. Okay, and also they propose the concept saying that this black body radiated waves are moving like a stationary waves. Okay, so for example, they took the concept of saying that the waves are, suppose the waves are starting from here. Okay, it goes and then it gets bounced back, and then it can retrace its path and form a stationary wave. Okay, so this is for a full wavelength lambda. Okay, or it can form, because the waves have to end in the nodal position. Okay, so in acoustics and in the stationary wave concept that you have studied in your class 12 book, you can see this. Okay, it is a full wavelength lambda which is confined within the region of x is equal to 0 to x is equal to a. So for a length of a, this is a wavelength lambda. Okay, or the wave can also be like this, as this way, isn't it? So it is lambda by 2 in this case. Okay, so it is half. It can form a stationary wave pattern like this. Okay, so I can say that like this is along the wave propagation along the x side. There may be many waves that can propagate along the y or along the z direction, and there may be n number of waves, and n number of waves. For example, suppose you take the waves that are traveling along x direction. Okay, how many number of waves may be formed and how they will propagate? How many modes of vibrations are possible within that particular length of x region? Similarly, you will have to calculate for the y region. You may have to calculate for the z region. And then you have to add it up together. and then find, okay, how many modes of radiations are possible inside a particular cavity. Okay, so we need to calculate how many, okay, how many modes of vibrations are possible within the black body cavity. So we consider this as a cavity here. Okay, so we need to find the number of modes of vibration which are possible in an unit area. Okay, in an unit area you need to calculate, and then you can calculate, summarize it for the entire region. Okay, so as I said before, so for a particular E is equal, so on this both the side the energy is 0. Okay, and this is x is equal to 0, x is equal to a. Okay, so a wave can be formed like this. Okay, this is a wave that has, okay, that ends with the two nodes on the two edges. Okay, so this is a longest possible wave. Okay, this is a longest possible wave. Okay, in between the length x is equal to 0, okay, and x is equal to a. X is equal to 0 and x is equal to a. Okay, so I can put it in as an equation as a is equal to, okay, lambda x by 2. Okay, and what is the next possible wave? The next possible wave can be like this. Okay, the next possible wave can be this way. Okay, this I can write it as a. Okay, the relation between the distance and the wavelength are put up like this. Okay, and a I can write it as 2 lambda x by 2. And for the wave that is like this, okay, the third one, okay, so it will be a is equal to 2 lambda x by 2, or the third one is, if the wave is having a pattern like this. Okay. Okay, this one I can write it as a is equal to 3 lambda x by 2. Okay, so it will go on like this. Okay, so a can be 3 lambda x by 2. The shorter the waves becomes, you will have 4 lambda x by 2 and so on. Okay, is it clear? Okay, where n here refers to the integer as nx is equal to 1, 2, 3, etc. Now, our interest is to find the, as I said, our interest is to find the mode of radiations. Okay, how many modes of radiations are possible within a particular unit area. Okay, so keep that in mind. So we need to now calculate for the y and the z direction also, isn't it? Now this is for x, x, x. Okay, so similarly, if I approximately take it for all the waves traveling along y direction, okay, what will be the equation? Okay, for all the waves that is traveling in the similar way. Okay, imagine that there are waves traveling along, okay, this way. For x is equal to 0 to x is equal to a, imagine that the wave is like this, or the wave can be like this way, or the wave can be like, okay, this way. Okay, so these are the waves that are traveling along y directions. So I can write it as ay in general. I can write it as ny z y by 2. Okay, now this is for z, no? Lambda y, sorry, lambda y by 2. Okay. Similarly, for the wave traveling along z direction, I will write it as az is equal to nz lambda z by 2. Okay. So here I will approximate as nx lambda x by 2. This is for all the waves that are propagating along the x direction. This is for the y direction, and this is for the z direction. Okay, z direction, I have to write it here. Az is equal to nz lambda z by 2. Okay. Now, there may be waves traveling arbitrarily along the other direction. If we are going to talk about a wave, we cannot confine and say that the wave has to travel only along x direction, only along y direction, or only along z direction. The wave can travel anywhere in between the xy direction, or in between the y and z direction, or y and x direction, isn't it? So when we consider such waves, we need to consider the angle also into account. Okay, so let's consider alpha, beta and gamma are the angles that are subtended. Okay, so let this be the x, y, this be the z direction. Okay, and let's imagine, okay, that this will be the alpha, this will be the beta, and gamma is between the other two directions. Okay, so in that case, a wave can travel along this way, okay, or it can travel the entire one like this, or it can travel like this also. Okay, or sometimes a wave can be traveling in between like this, isn't it? It can also travel like this between the z and the y direction, or between z and the x direction. Okay, in that case, these waves also have to be taken with the particular angle between them. Okay, so when we include the angle factor, okay, so when we start including the angle factor, okay, we have to include the angle factor of alpha, beta and gamma. Okay, so therefore the equation now will become, okay, nx will be equivalent to, okay, I have to write it as 2a by lambda, okay, into cos alpha, and the waves traveling, the number of waves traveling along the y direction will become ny is equal to 2a cos beta by alpha, and then nz will become 2a cos gamma by lambda. Okay, are you able to see it? Okay, so otherwise I will write it over here. Nz will be 2a cos gamma by lambda. Okay, so putting all these things into equation, okay, putting all these things into the equation, I have nx, ny and nz, number of waves traveling along the x direction with a particular angle, number of waves traveling along the y direction with a particular angle of beta, and number of waves traveling along the z direction with a particular wave of angle of gamma. Okay, so adding up all these things, because I need to know the number of waves, their mode of, the mode of vibrations I need to know per unit area. So first I need to know the number of waves. So I need to calculate nx, ny and z. I have to add up all these things together. Okay, so when I add all these factors together, okay, so let us summarize. Okay, so you can give the equation number. I have given it in the notes and I will send it to you. Okay, so when I add up this equation nx, okay, square up and add this equation for convenience sake. Okay, because you will find that cos square alpha cos square beta plus cos square gamma will become 1. So for that reason, nx square plus ny square plus nz square, you just add it up together. Okay, and then so it will become 2a by lambda cos alpha the whole square. Okay, plus next one is 2a cos beta by lambda the whole square plus 2a by lambda cos gamma whole square. Okay, so when I add this equation, take the 2a by alpha factor commonly outside. So 2a by lambda outside, the remaining one will be cos alpha square plus cos beta square. Okay, cos square beta, and then sorry, the square has to go inside this. Okay, then cos square gamma. Okay, and add up all these things equation, and this you know it is just nothing but 1 by Pythagoras theorem. So the answer will become, this will become n on one side. Okay, so it will become n is equal to 2a by lambda. Okay, and then when we substitute for this lambda in terms of frequency, okay, we know that lambda is equal to nothing but c by nu, isn't it? So substitute that value here. So lambda, I'm going to replace it as c, and gamma will come on the numerator. So on this side, okay, so this is still nx square only. This order 3 has to be written the same way. Nx square plus ny square plus nz square is equal to, okay, same thing, nx square plus ny square plus nz square is equal to this vector. Okay, block this equation and give an equation number as 1. Okay, so these are the possible modes of vibration that is possible in a Cartesian system of x, y, z. Okay, Cartesian coordinates meaning that they are in the x, y and z direction. Now we are going to consider this in another 3-dimensional coordinate system. Okay, we are going to take this entire thing into a 3-dimensional coordinate system, and then we are going to analyze this further, the mode of vibration. Okay, so I'll stop here because a huge file cannot be uploaded. So I'm going to stop here with this, and in the next video we will try to continue. Thank you.